So the topic of conversation in this video is Gibbs free energy. And so if you recall, we left off talking about entropy in the last video. So we're going to kind of pick up there and lead into the idea of Gibbs free energy. So taking a look at some practical uses. Now a lot of this is going to be derivation, so you don't have to worry too much about understanding exactly where it's coming from, but just how we kind of got there. So heat that flows into or out of a system also changes the entropy of the surroundings. And so the delta S of the surroundings is equal to the negative energy of the system divided by the temperature. So at constant pressure, since the Q of the system is also equal to delta H, we can say that the change in entropy of the surroundings is equal to the change in enthalpy divided by the temperature of the system. So that's the link between enthalpy and entropy. You can see that in phase changes. So in a phase change, it happens isothermally. There is no temperature change. So as the temperature increases at a phase change, what's the only thing that's happening? The entropy of the system is increasing. Remember, we're breaking IMFAs. We're taking those molecules and making them less rigid in their structure. So we're increasing the entropy even though the enthalpy is not changing. So for water, the delta H of fusion is 6 kilojoules. For the delta H of vaporization, it's 41 kilojoules. It takes a lot more energy to break all those IMFAs and give lots and lots and lots of microstates to those free molecules than it does to simply take the solid form and make it liquid, so they're still close together. They're just kind of doing a little bit more rotating and so forth. If we do this reversibly, then the delta S of the system is equal to the negative delta S of the surroundings. So still in the idea of derivation. So the universe is composed of system and surroundings. The delta S of the universe is obviously equal to the delta S of the system plus the delta S of the surroundings. So if the system's decreasing in entropy, the surroundings must be increasing entropy and vice versa. For a spontaneous process, the delta S of the universe has to be greater than 0. Because for it to be spontaneous, it has to happen automatically. You have to increase the number of microstates. All right, so we can say, like we said in the last slide, the delta S of the universe is equal to the entropy of the system plus the entropy of the surroundings. And remember that the entropy of the surroundings is equal to the negative delta H of the system divided by T. So we're going to plug that in there. So now we have system and system. Okay, so now we've got this version of the equation. And then we're going to take this temperature and make it a little bit more easy in a question. So notice we're multiplying through by T. So we've got T delta S of the universe equals T delta S of the system minus the delta H of the system. Okay, so we're getting to Gibbs free energy. So this is the equation we had on the last slide. This is actually equal to the negative Gibbs free energy. So I know we haven't defined Gibbs free energy, but we're showing how you derive it. So T delta S of the universe is equal to the negative Gibbs free energy. So if we make the equation look a little bit better, we're going to, since this is negative Gibbs, we're going to make this positive Gibbs and call it negative T delta S. Make this negative, make this positive. So we're going to change the signs of everything. And we got the Zamboni in the hallway making lots of noise. So that brings us to this equation of Gibbs free energy, delta G, Gibbs free energy, is equal to delta H of the system minus T delta S of the system. So this is, notice it's surrounded by 3 colors. This is the equation that we want to use. So for a spontaneous process, delta S of the universe has to be greater than 0. Delta H of the universe has to be less than 0. So minus T delta S of the universe is defined as Gibbs free energy for a spontaneous process. So therefore, for a spontaneous process, delta G has to be less than 0. So delta G has to be negative if the reaction is going to be spontaneous. Okay, so delta G is actually a lot easier to determine than delta S. So we use delta G to decide spontaneity as opposed to delta S. So what is this Gibbs free energy? Gibbs free energy is the energy associated with the chemical reaction that can be used to do work. Okay, so it combines both driving forces, enthalpy and entropy. So it's the amount of energy that can be used to do work. That's really important, especially in biological processes where we have to pull energy out of the chemicals that are taken into our bodies in order to do all of the life functions that keep us alive. So the change in free energy of a stem that occurs during a reaction measures the balance between a stem. There's got to be a typo there, and I can't think of what it is. Measures the balance between these two driving forces. Of a system, I think that's supposed to be, that occurs during a reaction, measures the balance between two driving forces, and this is what determines spontaneity. So here's a graphical example. So if delta G is negative, that means the forward reaction is spontaneous. So it's going to go, so the amount of free energy is going to decrease as I move from reactants to products. So I'm losing energy from the reactants as the reaction progresses. When I hit this bottom point where delta G is equal to 0, that's where the system is at equilibrium. So it can go either way. And then if delta G is positive, that means the reaction is non-spontaneous for the forward. It must be spontaneous for the reverse. So at this lowest point is where you have the equilibrium. And notice we've got K's and Q's here. We're going to get to that probably on the next set of slides that we take a look at. So we can also talk about standard free energy. Standard free energies of formation in particular. So it's analogous to the standard enthalpies of formation. So standard meaning at 25 degrees Celsius and 1 atm. We can set up an equation very similar to what you saw for the heat of formation. Wait a second. Should that be products minus reactants? I'm thinking there's a typo in that. Yep, this should be products minus reactants. So I just realized that this is wrong. This should be some of the delta G's of the products minus some of the delta G's of the reactants. Because the same equation that you can use to get delta H and delta S, you can also use to get delta G's. If you know all the delta G's of the various components, you can get the delta G of formation. We can look it up in tables, or we can calculate them from the standards if you know what delta S and delta H are. So you can use the delta G equals delta H minus T delta S equation, or simply by knowing what all the delta G's of the components are. Two ways to do it. So the very key equation is the one that I just got done telling to you, the one that's surrounded by 3 colors. This is the one that we're going to use most often. And this equation shows how delta G changes with temperature. So temperature is actually a very important component of whether or not the reaction is going to take place spontaneously. There are some reactions where temperature is critical. Lower temperatures mean one thing, higher temperatures mean something else in terms of spontaneity. So one of the assumptions that we make is that entropy and enthalpy are independent of temperature. It's not completely true, but that's the assumption that we make in this situation. So there are 2 parts to the free energy, the delta H, the enthalpy term, and the T delta S, the entropy term. So the temperature dependence of free energy really comes from the entropy term. So you can think of, if I have a higher temperature, I'm more likely to have a substance as a gas, which means there's a greater entropy involved. If I have a low temperature, chances are I might have more solids, and so then there's less entropy involved. So that's why the temperature is attached to the entropy idea. So here's a really nice summary of being able to predict whether or not the reaction is going to be spontaneous. So for it to be spontaneous, remember we want delta G to be negative. If delta G is negative, it's going to be spontaneous no matter what the temperature is, because delta H is negative, delta S is positive. These are the two components that we want to be, that imply spontaneity. You want a system to lose energy and you want it to increase in entropy. So regardless of what the value of temperature is, you wind up with a negative value for delta G. If you do the exact opposite, where delta H is positive, so it's an endothermic process, requires energy from somewhere else, and you're decreasing the entropy, that means you have a non-spontaneous reaction at most temperatures, at all temperatures. Most reactions don't fit one of these two categories. However, most reactions fall here. So temperature does matter. So if you are spontaneous with respect to enthalpy, but non-spontaneous with respect to entropy, you want the temperature to be very low, and you can work this out using that equation. You want the temperature to be low in order to have the delta H overwhelm that delta S. Conversely, if delta H is positive, you want and delta S is positive, so delta S is the spontaneous part, you want this part to be big, so you want to have a very, very high temperature in order to allow this component to outweigh the positive delta H. So just remember, spontaneity means that the delta G is negative overall in order to be spontaneous. So here's an example. You've got a particular reaction with these values. Notice that delta H is in kilojoules, delta S is in joules per Kelvin. So one thing is you have to have the temperature in Kelvin, and to add these two together, you need the same units of joules or kilojoules. So make sure you're paying attention. Okay, so we're going to use this equation. I've got 24 kilojoules here for the delta H. I've got 132 joules per Kelvin, so I've got to convert that to kilojoules, so 0.132 kilojoules times 298 winds up giving me a delta G of negative 14.7, so will it be spontaneous? Yep, because it's negative, it's going to be spontaneous. That is actually the last slide that I want to do with Gibbs free energy. So again, the derivation gets us to the equation, but it's really the equation that's the important part. But since free energy talks about spontaneity and equilibrium talks about spontaneity, our next video is going to merge those two ideas into one.